Well. Sit down, my dear friend. Let me tell you a story that your history books probably skipped over. A story about a German engineer who literally changed the way you eat, drink, and live every single day of your life. And I bet you don't even know his name, do you? His name was Carl von Linde, and in 1876, I was right there in Munich watching this brilliant madman create what would become the backbone of modern civilization. You see, back then, if you wanted ice, you had to wait for winter and hope the lake froze thick enough to cut blocks from it. Can you imagine? No ice cream in summer, no cold drinks, no fresh meat that lasted more than a day in the heat. But Carl had a different idea. A crazy, impossible idea that everyone thought would never work. He wanted to make ice with a machine, with chemistry, with ammonia. Of all things, people thought he was absolutely insane. Chapter 1. The Munich Workshop of Dreams and Disasters. I remember it like it was yesterday. Munich, 1876. The summer was brutal that year, the kind of heat that made your clothes stick to your skin and turned fresh milk sour within hours. I was working as a young apprentice in the industrial district, and word had spread about this professor at the technical university who claimed he could make winter in the middle of summer. Carl von Linde wasn't just any professor, mind you. This man had already made a name for himself studying gases and thermodynamics. But when he started talking about artificial refrigeration, even his colleagues began to whisper behind his back. The heat has gotten to old Carl, they'd say. He's lost his mind. But I was curious. You know me. I've always been drawn to the impossible, the crazy, the revolutionary. So one sweltering afternoon in July, I made my way to his workshop on Maximilianstrasse. The moment I stepped inside, I knew I was witnessing something extraordinary. The workshop was a maze of copper pipes, glass vessels, and strange mechanical contraptions that hissed and bubbled like a witch's cauldron. The air reeked of ammonia, that sharp, nose-burning smell that made your eyes water. Most people would have run out immediately. But Carl was standing in the middle of it all, with the biggest grin I'd ever seen. "Young man," he called out to me in his thick Bavarian accent. Come and witness the future." He was wearing a stained white coat, his gray hair wild and unkempt, his spectacles fogged up from the steam rising from his apparatus. He looked like a mad scientist from one of those penny novels, but his eyes burned with the fire of discovery. I approached cautiously, my nose twitching from the ammonia fumes. "Professor," I managed to say, "what exactly are you trying to do here?" He laughed, a sound like thunder rolling across the Alps. "What am I trying to do? My boy, I'm trying to steal winter itself. I'm going to make ice when the thermometer reads 35 degrees Celsius outside." Now you have to understand, this was 1876. The very idea of mechanical refrigeration was not just novel, it was revolutionary. Sure, there had been some experiments with ice-making machines in America and Britain, but they were massive, expensive, and mostly unsuccessful. Most people still relied on natural ice, which was harvested from frozen lakes and rivers during winter and stored in insulated ice houses. The ice trade was huge business back then. In America, a man named Frederick Tudor, they called him the Ice King, had made a fortune shipping ice from New England to the Caribbean and even to India. Can you imagine? Sailing ships loaded with blocks of frozen water, racing against time and temperature to deliver their precious cargo before it all melted away. But Carl von Linde had a different vision. Instead of depending on nature's whims and the grueling labor of ice harvesting, he wanted to create a machine that could produce ice on demand, anywhere, anytime. It was ambitious beyond belief. "Look here," he said, leading me to a complex arrangement of pipes and cylinders. "This is an ammonia compression system. Watch closely." He adjusted several valves, and suddenly the machine came to life with a mechanical symphony of hisses, clicks, and whirs. "The principle is simple," he explained, though nothing about it looked simple to me. Ammonia gas has remarkable properties. When you compress it under pressure, it becomes liquid and releases heat. And when you allow it to expand back into gas, it absorbs heat from its surroundings. By controlling this process, we can literally move heat from one place to another. I nodded as if I understood, but honestly, it felt like listening to a wizard explain magic spells. The science behind it was completely beyond my comprehension at the time. All I knew was that this strange machine was making the air around certain pipes noticeably colder, even as the Munich summer blazed outside. "But Professor," I asked, "if this works, why isn't everyone doing it?" His expression grew serious. "Because, my young friend, the challenges are enormous. Ammonia is toxic. One leak could kill everyone in this room. The pressures involved are dangerous. The pipes could explode at any moment. The machinery is complex and expensive. And even if we solve all these problems, who's going to trust a machine over methods that have worked for thousands of years?" As if to emphasize his point, at that exact moment, a loud hissing sound erupted from somewhere behind us. Carl's eyes went wide, and he shouted, "Get down!" We both dove behind a workbench just as one of the copper joints gave way, releasing a cloud of ammonia gas into the air. The smell was overwhelming, like being punched in the face by an invisible fist made of cleaning solution. My eyes streamed with tears, and my throat burned as if I'd swallowed fire. Carl was already on his feet, scrambling to shut off valves and stop the leak, his hands working with practiced precision despite the chaos. "This," he shouted over the noise of escaping gas, "this is why people think I'm crazy." But even as we both coughed and gasped, even as the workshop filled with toxic fumes, I could see something in his eyes that never wavered. Absolute, unwavering determination. This man wasn't going to give up, no matter how many pipes exploded, no matter how many times his colleagues called him insane. After we'd ventilated the workshop and the immediate crisis had passed, Carl sat down heavily on a stool, looking every one of his 43 years. "You know," he said quietly, "my wife thinks I should give up this foolishness and focus on more practical research. My colleagues at the university are starting to question my judgment. Even my students sometimes look at me like I've lost my mind." "So why don't you?" I asked. "Why keep risking your reputation, your safety, your career for this?" He was quiet for a long moment, staring at his damaged apparatus. Then he looked up at me with an intensity that I'll never forget. "Because I can see the future, boy. I can see a world where every home has an icebox that never runs empty, where meat doesn't spoil in the summer heat, where medicines can be kept cold and effective, where people can enjoy a cold drink on the hottest day of the year, where entire industries can be born around the ability to control temperature. I can see ships carrying fresh food across oceans without spoilage. I can see factories that never have to shut down because of heat. I can see hospitals keeping life-saving drugs stable in any climate. All of this is possible if we can master the science of artificial cold." His voice was rising with excitement now, and I found myself getting swept up in his vision. "But most importantly," he continued, "I can see the end of want, the end of families going hungry because their food spoiled, the end of entire communities suffering from spoiled medicines, the end of industries being held hostage by the weather." That was the moment I truly understood Carl von Linde. He wasn't just trying to make ice, he was trying to make the world a better place. And if that required risking his reputation, his safety, and his sanity, then so be it. Chapter 2. The Science of Stealing Heat. Over the following weeks, I became Carl's unofficial assistant. I swept his workshop, organized his tools, and most importantly, I listened. Carl loved to talk about his work, and I was a captive audience for his theories about thermodynamics and the behavior of gases. "The key to understanding refrigeration," he explained one morning as we cleaned ammonia residue from a burst pipe, "is to stop thinking about cold as something we create. Cold is simply the absence of heat. What we're really doing is moving heat from where we don't want it to where we don't mind it." He drew diagrams on every available surface, the workshop walls, scraps of paper, even in the dust on his workbench. "Look at this cycle," he said, sketching frantically. "The ammonia starts as a gas at low pressure. We compress it with a pump, which forces the molecules together and turns it into a liquid. This compression generates heat, which we get rid of using cooling coils. Then, and this is the beautiful part, we allow the liquid ammonia to expand through a valve back into a gas. As it expands, it needs energy to break apart the molecules, and it steals that energy in the form of heat from whatever is around it. If we do this inside an insulated box, the ammonia steals heat from inside the box, making it cold. The elegance of it was breathtaking, even if the practical implementation was proving to be a nightmare. Every day brought new challenges. The ammonia would corrode certain metals, so Carl had to experiment with different alloys for his pipes. The pumps would seize up from the strain of compressing the gas. The insulation materials of the time were primitive and ineffective. But Carl's biggest challenge wasn't technical, it was economic. Building these machines was expensive, and finding investors who understood the potential was nearly impossible. I remember the day Baron von Hirsch visited the workshop. He was a prominent Munich businessman who had made his fortune in textiles, and Carl had managed to convince him to consider investing in the refrigeration project. The Baron arrived in an elegant carriage, dressed in an immaculate black suit despite the summer heat. He was a thin, stern-looking man with a perfectly waxed mustache and the kind of calculating eyes that could spot a profitable investment from across a room. Carl was nervous, more nervous than I'd ever seen him. He'd spent the previous 3 days preparing a special demonstration, fine-tuning every component of his latest machine until it ran like clockwork. The workshop had been cleaned until it gleamed, and Carl had even trimmed his unruly hair and beard for the occasion. Baron von Hirsch, Carl began formally, "Thank you for coming to see what I believe will revolutionize industry and commerce throughout the German states and beyond." The Baron nodded curtly, his eyes already scanning the apparatus with obvious skepticism. "Professor Linde, I'll be frank with you. I've heard some very interesting claims about your work, but I've also heard that you're attempting something that violates the laws of nature. I'm here to see which version is true." Carl's confidence seemed to return at the challenge. "Baron, what I'm about to show you doesn't violate natural law. It harnesses natural law in a way that's never been done before on a practical scale. Please observe." The demonstration began flawlessly. Carl's machine hummed to life, its various components working in perfect harmony. The ammonia circulated through the system, and within minutes, frost began to form on the evaporator coils. The Baron watched with growing interest as the temperature inside the test chamber dropped steadily. "Remarkable," the Baron murmured, reaching out to feel the cold air flowing from the machine. "The ambient temperature must be 30 degrees, yet this chamber feels like it's barely above freezing." "Exactly," Carl exclaimed. "And this is just a small demonstration model. Imagine machines 10 times this size, powerful enough to freeze entire rooms of food, or to keep brewery cellars at perfect temperatures year-round, or to preserve medicines and chemicals that currently spoil in warm weather." The Baron was clearly intrigued, but being a shrewd businessman, he began asking the hard questions. What about the cost? What about reliability? What about safety? I've heard stories about ammonia leaks killing workers in American ice plants. Carl had anticipated these questions and had prepared detailed answers. He explained his innovations in safety valves, his improvements to pipe joining techniques, his calculations on operating costs compared to natural ice. For every concern the Baron raised, Carl had a solution, or at least a reasonable plan to develop one. But then the Baron asked the question that Carl hadn't fully anticipated. "Professor, who exactly is going to buy these machines? The ice trade is well established, reasonably reliable, and familiar to everyone. Why would someone risk their money on an untested technology?" Carl was quiet for a moment, and I could see him thinking furiously. Finally, he said, "Baron, let me tell you about the Munich brewery that lost an entire season's production last summer because the natural ice ran out in July. Let me tell you about the butcher on Marienplatz who has to throw away half his meat every week because he can't keep it fresh. Let me tell you about the pharmaceutical company that can't expand their operations because they can't guarantee their products will remain stable during shipping. These aren't theoretical problems, Baron. They're real businesses losing real money every day because they can't control temperature. My machine doesn't just make ice. It makes reliability. It makes predictability. It makes it possible for businesses to operate year-round without being held hostage by the weather." The Baron was nodding slowly, and I could practically see the calculations running through his head. He understood profit and loss, supply and demand, market opportunity. And what Carl was describing was a massive market opportunity. But then, at the worst possible moment, disaster struck. One of the ammonia lines, stressed from the extended demonstration, chose that exact instant to fail. There was a loud crack, followed by the familiar hissing sound of escaping gas, and suddenly the workshop was filling with toxic fumes. Carl and I knew the drill by now. Shut off the valves, open the windows, get everyone to safety. But the Baron had never experienced an ammonia leak before. The smell hit him like a physical blow, and he staggered backward, gasping and covering his face with his handkerchief. "Get him outside!" Carl shouted over the noise of escaping gas. I grabbed the Baron's arm and pulled him toward the door as Carl worked frantically to stop the leak. By the time we got the Baron to fresh air, he was pale and shaken, his perfect composure completely shattered. "This," he gasped, still trying to catch his breath, "this is what you call safe." Carl appeared in the doorway, his face grim. The leak was sealed, but the damage was done. The Baron's confidence in the technology had evaporated along with the ammonia. "Baron, please," Carl began. "This was an isolated incident. The safety protocols I've developed." But the Baron was already walking toward his carriage. "Professor Linde," he called back over his shoulder, "when you have a machine that doesn't try to kill its investors, please feel free to contact me again." As the carriage disappeared down the street, Carl sank onto the workshop steps, his head in his hands. 6 months of work," he muttered. 6 months of preparation, and it all comes apart in 60 seconds. "Professor," I said, sitting beside him, "maybe this isn't the end. Maybe this is just how these things work. 1 step forward, 2 steps back, but always moving toward the goal." He looked up at me with tired eyes. "You have more faith in this project than I do sometimes. Boy, some days I wonder if everyone else is right, if I really am chasing an impossible dream." "But you've already proven it works," I insisted. "The machine was making ice. It was colder than winter inside that chamber, and it was 30 degrees outside. That's not a dream, that's reality." Carl was quiet for a long moment, staring at his hands. Then slowly, a smile began to creep across his face. "You know what, boy? You're absolutely right. The science works. The principle is sound. All I need to do is solve the engineering problems, and engineering problems can always be solved with enough time and persistence. Besides," he added, standing up and brushing off his coat, "I've got something the Baron doesn't have. I've got you to help me clean up the mess every time something explodes." And so we went back to work. Every morning, Carl would arrive at the workshop before dawn, and every evening, he would stay until long after dark. He redesigned his ammonia handling systems. He improved his safety valves. He experimented with different compression ratios and cooling configurations. I watched him work with the dedication of a monk and the precision of a master craftsman. Every failure taught him something new. Every explosion revealed a weak point that could be strengthened. Every leak showed him how to build better seals. What I didn't realize at the time was that Carl was methodically solving every problem that had plagued mechanical refrigeration since its inception. He was creating not just a working machine, but a reliable, safe, practical system that could be manufactured and operated by ordinary people. The breakthrough came on a cold morning in October. Carl had been working on a new valve design that would regulate ammonia flow more precisely. I arrived at the workshop to find him standing in front of his latest machine, which had been running continuously for 3 days without a single malfunction. "Boy," he said without looking up, "what's the temperature outside?" I checked the thermometer mounted on the workshop wall. 8 degrees Celsius, Professor." "And what's the temperature inside the refrigeration chamber?" I looked at the gauge he'd installed, minus 12 degrees Celsius. "So let me get this straight," Carl said, finally turning to face me with the biggest grin I'd ever seen. "It's 8 degrees outside, which is cold enough to make most people wear heavy coats. But inside this machine, it's minus 12 degrees, which is cold enough to freeze solid any food we put inside it. And the machine has been maintaining this temperature difference for 72 hours straight without any human intervention." I nodded, beginning to understand the magnitude of what we were witnessing. "My boy," Carl said, I do believe we've just changed the world. Chapter 3: The First Customer and the Birth of an Industry. Word of Carl's success began to spread through Munich's industrial community like ripples in a pond. Engineers, businessmen, and curious onlookers started appearing at the workshop, drawn by rumors of the ice machine that actually worked. But Carl was cautious about demonstrations now. He'd learned from the Baron von Hirsch incident that timing was everything, and he wanted to be absolutely certain his machine was ready for public scrutiny. So he spent the winter of 1876 perfecting every aspect of his system, testing it under every condition he could imagine. I became his unofficial testing partner, helping him run the machine at different loads, different temperatures, different humidity levels. We deliberately subjected it to stress tests that would have destroyed his earlier models. We ran it continuously for weeks at a time. We even tried to break it in controlled ways, just to understand its failure modes. If this machine is going to fail, Carl would say, I want it to fail here in my workshop, where I can fix it, not in some customer's facility where a breakdown could ruin my reputation forever. By spring of 1877, Carl's machine was running with the reliability of a Swiss watch. It could produce over 200 pounds of ice per day while consuming less fuel than any competing design. More importantly, it had safety systems that would shut it down automatically if anything went wrong, preventing the catastrophic ammonia leaks that had plagued earlier refrigeration attempts. That's when Gabriel Sedlmayr showed up at our door. Now, if you've never heard of Gabriel Sedlmayr, you've probably heard of his family's business, Spaten Brewery. The Sedlmayrs were one of Munich's most successful brewing families, and Gabriel was the kind of forward-thinking industrialist who was always looking for new technologies to give him an edge over his competitors. I remember the day he first visited the workshop. Unlike Baron von Hirsch with his formal carriage and stiff manner, Gabriel arrived on foot, wearing practical clothes and carrying a notebook. He had the calloused hands of someone who actually worked in his own brewery, and his eyes held the sharp intelligence of a man who understood both the technical and business sides of industrial operations. Professor Linde, he said after introducing himself, I've been hearing remarkable stories about your ice machine. As someone who spent most of his life fighting the problems caused by temperature control in brewing, I'm very interested in what you've accomplished. Carl was immediately intrigued. Brewing was one of the industries that suffered most from temperature variations. Beer had to be fermented at specific temperatures, aged at others, and stored in consistently cool conditions. Most breweries could only operate effectively during cooler months, and even then, they were at the mercy of natural temperature fluctuations. Mr. Sedlmayr, Carl replied, I believe I may have exactly what you're looking for, but before I show you my machine, tell me about your specific challenges. What problems are you trying to solve? Gabriel's face lit up. This was clearly a subject he was passionate about. Professor, where do I even begin? In summer, we can barely keep our fermentation temperatures stable. We lose entire batches when heat waves hit unexpectedly. Our aging cellars, even though they're underground, still fluctuate too much for optimal beer production. We spend a fortune on natural ice, and half the time it's poor quality or arrives late or melts before we can use it. But the real problem, he continued, is that we can't expand. There's growing demand for our beer, especially in warmer climates, but we can't guarantee consistent quality without consistent temperature control. I've been looking at brewery operations in America and England, and the ones that are succeeding on a large scale all have one thing in common: reliable refrigeration. Gabriel closed his notebook and extended his hand to Carl. Professor Linde, I believe we have a deal. When can you start installation? And just like that, Carl von Linde had his first commercial customer. But more than that, he had validation that his invention wasn't just a clever scientific curiosity, it was a viable commercial technology that could solve real business problems. The installation at Spaten Brewery took 3 months and nearly killed both Carl and me from exhaustion. We had to fabricate custom components, solve installation problems that had never been encountered before, and train brewery workers to operate and maintain equipment they'd never seen before. But when we fired up the system for the first time in Gabriel's fermentation room and watched the temperature drop steadily to exactly the level he wanted, and then watched it stay there day after day with rock-solid stability, I knew we were witnessing the birth of a new industry. Gabriel was ecstatic. Within weeks of the installation, he was achieving fermentation consistency he'd never dreamed possible. His beer quality improved dramatically, his production waste dropped to nearly zero, and he was able to extend his brewing season to year-round operation. More importantly, word of Gabriel's success spread throughout Munich's brewing community like wildfire. Within 6 months, Carl had inquiries from a dozen other breweries, not just in Bavaria, but throughout the German states. "Boy," Carl said to me one evening as we walked home from another successful demonstration, "I think we may have accidentally started something big." He had no idea how big. Chapter 4: The Ice Wars and Industrial Revolution. By 1878, Carl's workshop had evolved from a chaotic laboratory into something resembling a proper manufacturing facility. Word of the Spaten brewery's success had spread far beyond Munich, and orders were pouring in from breweries, meat packers, and even some ambitious entrepreneurs who wanted to start artificial ice companies. But success brought new challenges that Carl hadn't anticipated. The established ice trade, which had been operating profitably for generations, suddenly saw mechanical refrigeration as an existential threat, and they weren't going to give up their lucrative monopoly without a fight. I remember the morning when Heinrich Weber showed up at our door. Weber was one of Munich's most successful ice merchants, a man who controlled the natural ice trade throughout Bavaria. He was wealthy, well-connected, and absolutely ruthless in business. The kind of man who could make life very difficult for anyone who threatened his profits. "Professor Linde," he said, his voice deceptively pleasant, "I understand you've been having some success with your mechanical ice-making contraptions." Carl was immediately on guard. He'd heard stories about Weber's business practices, how he'd driven competitors out of business through price wars, exclusive contracts, and sometimes less savory methods. "Mr. Weber, thank you for visiting. How can I help you today?" "Well, Professor, I'm here to make you an offer. A very generous offer." Weber reached into his coat and pulled out a thick envelope. "This contains enough money to fund your research for the next 10 years, with no strings attached. All I ask in return is that you focus your considerable talents on more academic pursuits and leave the ice business to those of us who understand it." The workshop fell silent. Even the ammonia compressor seemed to pause in its rhythmic cycling. Carl stared at the envelope for a long moment, then looked up at Weber with an expression I'd never seen before, a combination of anger and disgust. "Mr. Weber," Carl said quietly, "I believe you've misunderstood what I'm doing here. I'm not in the ice business. I'm in the business of solving problems that have plagued humanity for centuries. I'm trying to make it possible for people to preserve food, improve industrial processes, and generally make life better through the application of scientific principles. The fact that my work threatens your particular business model is regrettable, but it's not my primary concern. Progress waits for no one, Mr. Weber, and what I've created here represents genuine progress." Weber's pleasant facade disappeared instantly. "Professor, I don't think you understand how business works in the real world. The ice trade employs thousands of people throughout Bavaria: ice harvesters, transporters, storage facility workers, distributors. Your machines will put all of these people out of work. Moreover, my customers depend on me for reliable service. I have contracts with breweries, restaurants, hospitals, and private homes throughout the region. If I can't meet those contracts because mechanical ice making has disrupted the natural ice supply chain, a lot of very important people are going to be very unhappy. And when important people are unhappy, Professor, they tend to make life difficult for the people who caused their unhappiness. Permits can be delayed. Safety inspections can become very thorough. Raw materials can become hard to obtain. Skilled workers can find better opportunities elsewhere. Do I make myself clear?" Carl's jaw was clenched so tightly I thought his teeth might crack. "Mr. Weber, are you threatening me?" "Not at all, Professor. I'm simply pointing out the realities of business competition, but my offer still stands." He placed the envelope on Carl's workbench. Take the money, pursue your academic research, and avoid the unpleasantness that inevitably comes with disrupting established industries. After Weber left, Carl stood staring at the envelope for a long time. Finally, he picked it up, walked to the workshop's furnace, and threw it in. We watched in silence as the envelope and its contents turned to ash. "Professor," I finally said, "was that wise?" Weber wasn't bluffing about his influence. He could make serious trouble for us. Carl turned to face me, and I saw something in his expression that reminded me why I'd followed him into this crazy venture in the first place. "Boy, let me tell you something about progress. It's never convenient for the people who profit from the old ways. When Gutenberg invented the printing press, the scribes who made their living copying books by hand fought against it. When steam engines were invented, the people who owned horse-drawn transportation fought against them. And now that we've invented reliable mechanical refrigeration, the natural ice merchants are going to fight against us. But here's the thing about fighting progress. You always lose in the end. Not immediately, maybe not even quickly, but inevitably, because progress serves people's real needs better than the old ways, and eventually people figure that out. Weber can delay us, harass us, maybe even hurt us financially in the short term. But he can't stop what we've created, because what we've created is simply better than what came before. And in a market economy, better eventually wins. Carl's confidence was infectious, but it was also about to be tested in ways he never imagined. The first sign of trouble came when our suppliers started having problems filling orders. Copper tubing that had been readily available suddenly became back-ordered indefinitely. Steel components that we'd been buying from local machine shops were suddenly no longer manufactured. Workers that Carl had hired began finding better opportunities elsewhere, usually just as they were becoming proficient with refrigeration technology. It was clear that Weber was using his influence to make life difficult for us, but he was being subtle about it. Nothing could be traced directly back to him, but the pattern was unmistakable. Carl adapted with the resourcefulness of a born inventor. When copper became unavailable locally, he found suppliers in other cities. When local machine shops wouldn't take his orders, he bought his own machining equipment and trained me to operate it. When experienced workers left, he hired apprentices and taught them from scratch. "You know what Weber doesn't understand," Carl said one evening as we worked late to catch up on a backlog of orders, "is that obstacles make us stronger. Every problem he creates forces us to become more self-sufficient, more innovative, more resilient. He's actually helping us build a better business." And Carl was right. By forcing us to solve our own supply and manufacturing problems, Weber had inadvertently pushed us to develop capabilities that made us less dependent on others and more able to control our own destiny. But Weber wasn't finished. His next move was more direct and far more dangerous. It was a cold February morning in 1879 when I arrived at the workshop to find Carl standing in the ruins of what had been our main assembly area. Someone had broken in during the night and systematically destroyed months of work. Partially completed refrigeration units had been smashed beyond repair. Tools had been stolen or damaged. Most devastating of all, Carl's detailed engineering drawings, the accumulated knowledge of 3 years of development work, had been scattered, and many were missing. Carl stood in the middle of the wreckage, his face pale, but his jaw set with determination. "They think this will stop us," he said quietly. "They think that destroying our work will force us to give up." "Will it?" I asked, surveying the devastation. "No," Carl said, his voice growing stronger. "It will just make us more careful about protecting our work and more determined to succeed. But it also tells us something important. We're winning. People don't go to these lengths to stop something that isn't a real threat to their interests." The break-in had the opposite effect that Weber probably intended. Instead of discouraging our customers, it convinced them that mechanical refrigeration must be incredibly valuable if someone was willing to go to such lengths to stop it. Orders actually increased as word spread about the sabotage. More importantly, the Munich business community began to take sides. Gabriel Settelmeyer and other brewery owners who had benefited from Carl's technology started using their own influence to counteract Weber's pressure. They spoke to suppliers, recommended qualified workers, and generally made it known that they supported Carl's work. Professor Linde has revolutionized our industry, Gabriel declared at a meeting of the Munich Brewers Association. His refrigeration technology has allowed us to improve quality, reduce waste, and expand our markets in ways that were impossible before. Anyone who tries to prevent the advancement of such beneficial technology is working against the interests of progress and prosperity. Other voices joined in. Dr. Johann Nepomuk von Fuchs from the Academy of Sciences wrote a public letter praising Carl's work as a triumph of German engineering and scientific innovation. The Munich Chamber of Commerce passed a resolution supporting technological advancement that benefits local industry. Gradually, the tide of public opinion turned in our favor. Weber found his influence waning as more and more people recognized that mechanical refrigeration was not just a threat to the ice trade, but a benefit to society as a whole. The final blow to Weber's campaign came from an unexpected source: the weather itself. The winter of 1879 to 1880 was unusually mild throughout Bavaria. The lakes and rivers that normally provided natural ice barely froze, and what ice did form was thin, poor quality, and dangerous to harvest. By March, Munich's natural ice reserves were completely exhausted, and Weber found himself unable to meet his contracts. Meanwhile, our refrigeration machines continued operating flawlessly, producing high-quality ice and maintaining perfect storage temperatures regardless of the weather outside. Businesses that had installed our systems were unaffected by the ice shortage, while those that depended on natural ice faced serious problems. I'll never forget the day Weber came back to our workshop. He looked like a man who had aged 10 years in 10 months. His expensive clothes were rumpled, his usually perfect hair was unkempt, and his eyes held the defeated look of someone who had fought a war and lost. "Professor Linde," he said, his voice barely above a whisper, "I've come to discuss terms." "Terms for what, Mr. Weber?" Carl asked, though we both knew what he meant. "I want to discuss the possibility of collaboration. Perhaps I could become a distributor for your machines, or maybe we could work together to serve customers who need both natural ice and mechanical refrigeration." Carl was gracious in victory. "Mr. Weber, I'm always open to working with people who are committed to serving customers' needs effectively. But I need to be clear about something. The future belongs to mechanical refrigeration. Natural ice will always have some applications, but it will be a shrinking market as our technology becomes more widespread and affordable. If you want to work with us, you need to understand that you're not just changing your business model, you're joining a technological revolution that will transform entire industries." Weber nodded slowly. "Professor, I spent most of this past year trying to stop that revolution. I failed, obviously. But maybe it's not too late for me to be part of it instead of fighting against it." And so Heinrich Weber, who had begun as our most dangerous enemy, became one of our most valuable partners. His knowledge of customer needs, distribution networks, and business operations helped us expand faster than we ever could have managed alone. Years later, Carl would often point to the Weber conflict as a perfect example of how technological progress ultimately benefits everyone, even those who initially oppose it. "Weber made more money as our partner than he ever did as an ice merchant," Carl would say, "and his customers got better service. Everyone won except the old, inefficient ways of doing things." But the victory over Weber was just the beginning. By 1880, word of Carl's refrigeration technology was spreading far beyond Bavaria, and orders were coming in from throughout the German states, Austria-Hungary, and even from other European countries. Carl realized that he needed to transform from an inventor with a workshop into an industrial manufacturer with a proper factory. It was a daunting challenge, but one that he approached with the same methodical determination that had made his refrigeration machines successful. Chapter 5: The Birth of the Global Refrigeration Industry. The transformation of Carl's workshop into a proper manufacturing facility was like watching a caterpillar become a butterfly, gradual at first, then suddenly spectacular. By 1881, what had started as a one-man laboratory had evolved into the Linde Ice Machine Company, with over 50 employees and a factory that could produce refrigeration systems for customers throughout Europe. But growth brought challenges that Carl had never anticipated. It's one thing to build a few custom machines for local breweries. It's quite another to manufacture standardized equipment that can be shipped across continents and operated by people you've never met. "Boy," Carl said to me one morning as we surveyed the bustling factory floor, "I'm starting to think the engineering problems were the easy part. Now I have to figure out accounting, personnel management, international shipping, patent protection, and a dozen other things they never taught me in university." He was right to be concerned. As our success grew, so did the complexity of our operations. We were dealing with customers who spoke different languages, used different measurement systems, and had different technical standards. We were shipping delicate equipment across vast distances using transportation systems that were often unreliable. We were competing with imitators who were copying our designs and trying to undercut our prices. But perhaps the biggest challenge was something Carl hadn't expected. Success itself was creating demand faster than we could meet it. The problem wasn't just that we were getting more orders than we could fill, though that was certainly true. The real problem was that every successful installation created a dozen new inquiries. When the Augustiner Brewery in Munich installed one of our systems and saw their production efficiency double, word spread to every brewery in Bavaria. When the Bavarian State Railway started using our refrigerated cars to transport perishable goods, every railway company in Europe wanted to know about the technology. Most challenging of all, we were getting inquiries for applications that Carl had never considered when he first started working on artificial refrigeration. I remember the day Count von Zeppelin visited our factory. Yes, that von Zeppelin, the man who would later become famous for his dirigibles. In 1882, he was primarily interested in military applications of new technologies, and he had a very specific question about refrigeration. "Professor Linde," he said in his crisp Prussian manner, "I understand that your machines can maintain specific temperatures regardless of external conditions. Could such a system be adapted to preserve medicines and foodstuffs during long military campaigns?" Carl's eyes lit up immediately. Military logistics was one of those problems that everyone accepted as unsolvable. Armies had been losing soldiers to spoiled food and ineffective medicines for centuries. "Count, not only is it possible, but I believe it could revolutionize military operations. Imagine being able to keep medical supplies stable in tropical climates, or to preserve food during long sieges, or to maintain equipment at optimal temperatures regardless of weather conditions. How quickly could you develop such a system?" von Zeppelin asked. "Give me 6 months and a reasonable budget, and I'll build you a portable refrigeration unit that can operate under battlefield conditions." That conversation led to one of our most interesting development projects. Military refrigeration required everything our civilian systems provided, but with additional demands for portability, reliability under harsh conditions, and operation by personnel with minimal technical training. Carl threw himself into the challenge with typical enthusiasm. He designed compact systems that could be transported by wagon or even carried by hand. He created foolproof operating procedures that could be followed by soldiers in the field. He developed emergency repair kits that would allow basic maintenance without specialized tools. The first field test was conducted with a Bavarian army unit during summer maneuvers in 1883. I accompanied the equipment to provide technical support, and what I witnessed there convinced me that Carl's invention would eventually change far more than just brewing and food storage. The military unit we worked with was conducting exercises in the hills outside Munich during one of the hottest summers in memory. Under normal circumstances, they would have faced serious problems with food spoilage, heat-related illness, and degradation of medical supplies. But with our portable refrigeration units, they maintained fresh food for the entire 2-week exercise, kept critical medicines at proper temperatures, and even provided chilled water for soldiers suffering from heat exhaustion. The commanding officer, Colonel Hartmann, was amazed. Professor Linde, he told Carl after the exercises concluded, this technology could change the entire nature of military campaigning. Armies have always been limited by their ability to maintain supply lines for fresh provisions. With portable refrigeration, we could operate effectively in any climate for extended periods. More importantly, the success of the military applications opened up entirely new markets that we had never considered. If refrigeration could work under battlefield conditions, it could certainly work in tropical colonies, remote mining operations, scientific expeditions, and other challenging environments. Orders began pouring in from all over the world. The British colonial administration wanted refrigeration systems for hospitals in India. Mining companies in Africa needed equipment to preserve food and medicines in remote locations. Scientific expeditions requested portable units for preserving specimens. Even luxury steamships wanted refrigeration systems to provide high-quality dining for wealthy passengers during long ocean voyages. Each new application required modifications to our basic design, but Carl welcomed the challenges. Every new application teaches us something about the fundamental principles of refrigeration, he would say. The more diverse problems we solve, the better our understanding becomes, and the better our future designs will be. By 1884, the Linde Ice Machine Company had installations operating on every continent except Antarctica. We had customers in the United States, South America, Africa, Asia, and Australia. Our machines were preserving food in tropical climates where ice had never existed naturally, enabling industrial processes that had been impossible in warm regions, and generally making life better for people all over the world. But perhaps the most satisfying development was watching other inventors and engineers build upon Carl's work. The scientific principles he had established were inspiring innovations in related fields: air conditioning, industrial cooling, cryogenic research, even early experiments with frozen food preservation. You know, Carl said to me one evening as we reviewed reports from installations around the globe, when I started this project, I thought I was just trying to solve the problem of making ice reliably. I never imagined that I was laying the foundation for entire industries that would employ millions of people and improve life for hundreds of millions more. Is that good or bad? I asked. It's magnificent, he replied without hesitation. This is how progress really works. Not through grand plans or revolutionary manifestos, but through individuals solving specific problems and then discovering that their solutions have implications far beyond what they originally intended. Indeed, by the mid-1880s, mechanical refrigeration was no longer just Carl von Linde's clever invention. It had become an essential technology that modern society was rapidly becoming dependent upon. Restaurants could serve fresh seafood hundreds of miles from the ocean. Hospitals could store medicines that remained potent for months instead of days. Factories could operate in climates that had previously been too hot for certain industrial processes. Ordinary families could buy food in larger quantities and store it safely for extended periods. Most importantly, the global food system was beginning to transform. Fresh meat could be shipped from Argentina to Europe. Fruits and vegetables could be transported from tropical regions to temperate cities. Dairy products could be distributed over vast distances without spoilage. We were witnessing the emergence of what economists would later call the global food market, a system where agricultural products could be produced in the most suitable climates and then distributed worldwide without regard to local seasonal limitations. But as our success grew, so did the challenges of managing a rapidly expanding international business. Carl, who had always been most comfortable in his workshop surrounded by machines and technical drawings, found himself dealing with complex questions of international trade, patent protection, currency exchange, and cultural differences between markets. "I'm an engineer, not a businessman," he complained to me one particularly frustrating day when a shipment to India had been delayed by customs problems. A customer in America was threatening legal action over a patent dispute, and our main supplier in Hamburg was demanding payment in gold instead of marks due to currency instability. "Maybe it's time to hire some people who are businessmen," I suggested. Carl was quiet for a moment, considering the implications. Hiring professional managers would mean giving up direct control over aspects of the company that had always been his personal responsibility. But it might also free him to focus on what he did best, solving technical problems and developing new applications for refrigeration technology. You know, he said finally, that might be exactly what we need to do. I got into this business to advance the science of refrigeration, not to become an expert in international commerce. Maybe the best way to serve that original goal is to let other people handle the business side while I focus on the technical development. That decision marked another turning point in the evolution of our company. By 1885, Carl had hired professional managers to handle sales, marketing, finance, and operations, while he returned to his first love, research and development. It was the perfect arrangement. The business side was managed by people who understood markets, customers, and competition. The technical side was led by Carl, whose passion for innovation had never diminished despite all the commercial success. And it was just in time, because the next phase of refrigeration development was about to begin, and it would make everything we had accomplished so far look like a preliminary experiment. Chapter 6: The Science of Extreme Cold and Unexpected Discoveries. By 1886, Carl had established himself as the world's leading authority on practical refrigeration technology. His machines were operating successfully on every continent. His company employed hundreds of workers, and his innovations had spawned an entire industry. But Carl being Carl, success only made him more curious about the fundamental science behind what he had achieved. "Boy," he said to me one morning as we walked through the research section of our expanded facility, "we've proven that we can create temperatures well below the freezing point of water. But what if we could go further? What if we could create temperatures so cold that they change the fundamental properties of matter itself?" This was the beginning of Carl's exploration into what would later be called cryogenics, the science of extremely low temperatures. At the time, it was purely theoretical territory. No one knew what happened to ordinary materials when they were cooled to temperatures far below anything that occurred naturally on Earth. The conventional wisdom was that there were practical limits to how cold you could make things. Most scientists believed that around -100 degrees Celsius represented the lower boundary of useful refrigeration. Beyond that point, the theory went, the energy required to extract additional heat would become prohibitively expensive, and the technical challenges would become insurmountable. Carl, of course, saw this as a challenge rather than a limitation. "Think about it," he said as we examined his latest experimental apparatus. "Every major breakthrough in refrigeration has come from pushing beyond what people thought was possible. When I first started making ice with ammonia, everyone said it couldn't be done practically. When we began commercial operations, everyone said mechanical refrigeration would never replace natural ice. When we expanded internationally, everyone said the technology couldn't work in different climates and conditions. Every time, the experts have been wrong because they were thinking about limitations instead of possibilities. So why should we believe them when they say that extremely low temperatures are impractical?" Carl's approach to extreme cold research was typically methodical. Instead of trying to achieve the lowest possible temperatures immediately, he began by systematically exploring what happened to different materials as they were cooled progressively below normal refrigeration temperatures. The results were fascinating and completely unexpected. At -50 degrees Celsius, rubber became as brittle as glass. At -80 degrees, mercury, normally a liquid at room temperature, solidified into a metal that could be hammered like iron. At -100 degrees, ordinary air began to behave in strange ways, with some of its components condensing into liquids while others remained gaseous. But the most remarkable discovery came when Carl managed to reach temperatures below -180 degrees Celsius, cold enough to liquefy air itself. I'll never forget the day we first succeeded in producing liquid air. Carl had been working for months on a cascade refrigeration system, essentially multiple refrigeration cycles working in series, with each stage achieving lower temperatures than the previous one. The technical challenges were enormous. At extremely low temperatures, materials that worked perfectly well in normal refrigeration systems began to fail. Rubber seals became useless, lubricants turned solid, and thermal stresses caused components to crack or shatter. Carl had to redesign virtually every component of his system for operation at extreme cold. He developed new sealing techniques using metal gaskets instead of rubber. He created solid lubricants that remained effective at ultra-low temperatures. He designed expansion joints and flexible connections that could accommodate the extreme thermal contractions that occurred as temperatures dropped. The day of the first successful liquid air production, Carl had invited several prominent scientists from the University of Munich to witness the demonstration. He wanted independent verification of what we were achieving, and he was eager to share the scientific implications with people who could fully appreciate them. Professor Wilhelm von Bezold from the physics department was there, along with Professor Adolf von Baeyer from chemistry and several other distinguished academics. They arrived expecting to see an interesting demonstration of advanced refrigeration technology. What they witnessed instead was something that challenged fundamental assumptions about the nature of matter itself. Carl started up his cascade system, and we all watched the temperature gauges as they dropped steadily through ranges that had never been achieved artificially before. -50, -100, -150 degrees Celsius. At -183 degrees, something magical happened. The air itself began to condense into a pale blue liquid that collected in a specially designed container. We were literally watching the atmosphere turn into a liquid that we could pour, measure, and manipulate. Professor von Bezold was speechless. "Herr Linde," he finally managed to say, "you have just liquefied the very air we breathe. Do you understand the implications of what you've accomplished?" Carl smiled, but I could see the excitement burning in his eyes. "Professor, I'm beginning to understand them, but I suspect the real implications are far beyond what any of us can imagine right now." He was absolutely right. Liquid air turned out to have properties and applications that none of us had anticipated. For one thing, liquid air was an incredibly concentrated source of oxygen. When allowed to evaporate slowly, it produced oxygen gas that was much purer than anything that could be obtained through chemical processes. This had immediate applications in medicine, where pure oxygen could be used to treat respiratory ailments, and in industry, where high-purity oxygen could improve combustion processes. But even more intriguing was liquid nitrogen, which could be separated from liquid air and had even more remarkable properties. Liquid nitrogen was so cold that it could freeze almost anything instantly. Flowers dipped in liquid nitrogen became so brittle that they shattered like glass when touched. Rubber balls bounced like steel when cooled with liquid nitrogen, then became flexible again as they warmed up. The scientific community was electrified by these discoveries. Here was a new realm of physics and chemistry, where familiar materials behaved in completely unfamiliar ways. Research institutions around the world began requesting liquid air and liquid nitrogen for their own experiments. But Carl saw practical applications beyond pure scientific research. "Consider food preservation," he said during one of our planning sessions. "We can already extend the life of perishable foods significantly with conventional refrigeration. But what if we could freeze them so quickly and so completely that all biological processes stopped entirely? What if we could preserve foods not just for weeks or months, but for years?" This was the beginning of what would eventually become the frozen food industry, though it would take several more decades for the technology to become practical for consumer applications. Carl also recognized industrial applications for extreme cold. Certain manufacturing processes could benefit from ultra-low temperatures. Metals could be made more durable through cryogenic treatment. Precision instruments could be calibrated more accurately in extremely stable thermal conditions, and chemical reactions could be controlled more precisely at very low temperatures. Even more intriguing were the possibilities for scientific research itself. Astronomers realized that liquid air cooling could make their instruments more sensitive by reducing thermal noise. Physicists discovered that many materials exhibited completely different electrical and magnetic properties at cryogenic temperatures. Chemists found that reactions that were impossible at room temperature became feasible at extreme cold. By 1888, Carl's cryogenics research had evolved into a separate division of the company, with its own laboratory, specialized equipment, and dedicated research staff. We were not only manufacturing conventional refrigeration equipment, but also producing liquid air, liquid nitrogen, and specialized cryogenic apparatus for research institutions around the world. You know, Carl said to me as we reviewed the latest research results, when I started working on refrigeration 12 years ago, I thought I was just trying to solve the problem of keeping beer cold. Now I'm exploring the fundamental nature of matter at temperatures that don't exist naturally anywhere on Earth. It's been quite a journey. And where do you think it's leading? I asked. Carl was quiet for a moment, staring at a sample of liquid nitrogen that was boiling vigorously in its container as it absorbed heat from the warm laboratory air. I think we're just getting started, he said finally. Every temperature range we explore reveals new phenomena, new possibilities, new applications. There's no reason to think that will stop as we go even colder. Besides, he added with the grin I'd come to know so well, I'm starting to wonder what happens if we go in the other direction. If we can create extreme cold, why couldn't we create extreme heat in a controlled way? And if we can master both temperature extremes, what other aspects of matter and energy might we learn to control? It was a prescient question. Carl's work on refrigeration and cryogenics was indeed leading toward a much broader understanding of thermodynamics, heat transfer, and energy conversion, knowledge that would eventually contribute to developments ranging from power generation to space exploration. But in 1888, those applications were still decades in the future. For the moment, Carl was content to push the boundaries of cold, to explore the strange and wonderful behavior of matter at temperatures that had never been achieved before, and to continue solving practical problems through the application of scientific principles. Little did we know that his next major breakthrough would come not from pursuing extreme cold, but from a completely unexpected direction, and it would make him one of the wealthiest men in Europe. Chapter 7. The Liquid Gold Discovery. By 1890, Carl von Linde had achieved everything he had originally set out to accomplish, and much more. His refrigeration technology was transforming industries around the world. His cryogenics research was opening up entirely new fields of science, and his company had become one of the most successful engineering firms in Europe. But Carl being Carl, success only made him more curious about unsolved problems. And there was one particular problem that had been nagging at him for years, a problem that seemed completely unrelated to refrigeration, but that would ultimately prove to be his most valuable discovery. The problem was natural gas. Throughout the industrializing world, natural gas was considered more of a nuisance than a resource. Oil wells frequently produced large quantities of gas, along with the oil, but there was no practical way to transport or store the gas. Most oil companies simply burned it off at the wellhead, wasting enormous amounts of energy because they had no choice. Even in regions where natural gas occurred by itself, without oil, it was difficult to use effectively. Gas could be piped short distances to provide lighting and heating for nearby communities, but long-distance transportation was impossible with the technology available at the time. The fundamental problem was that natural gas, being a gas, occupied enormous volumes compared to liquid fuels. A given amount of energy in the form of natural gas required hundreds of times more storage space than the same amount of energy in the form of oil or coal. This made natural gas economically impractical for most applications. Carl had been thinking about this problem for years, but it was a conversation with Heinrich Weber, our former enemy turned business partner, that finally crystallized the solution in his mind. "Professor," Weber said during one of our monthly business reviews, "I've been getting inquiries from petroleum companies about refrigeration equipment for oil storage. They're having problems with oil thickening in cold climates, and they want to know if our heating systems could keep storage tanks at optimal temperatures." Carl's ears perked up immediately. Heinrich, that's interesting, but let me ask you something different. What if instead of trying to keep oil warm, we tried to make natural gas cold? Cold enough to turn it into a liquid? Weber looked puzzled. Why would anyone want to do that? Because, Carl said, his excitement building as the implications became clear, liquid natural gas would occupy only a tiny fraction of the volume of gaseous natural gas. If we could liquefy natural gas at production sites, transport it in liquid form, and then allow it to gasify again at consumption sites, we could create a global natural gas market similar to the global oil market. The more Carl thought about it, the more excited he became. Natural gas was abundant in many regions where it was currently being wasted. If it could be liquefied for transportation, it could be used anywhere in the world. The energy content was high, the combustion was clean compared to coal, and the potential market was enormous. But the technical challenges were formidable. Natural gas was composed primarily of methane, which remained gaseous at much lower temperatures than water or air. To liquefy methane, Carl would need to achieve temperatures around minus 160 degrees Celsius, colder than anything he had accomplished even in his most advanced cryogenics research. This is going to require everything we've learned about extreme cold, Carl told me as we began planning the research project, plus innovations we haven't even thought of yet. We're not just trying to liquefy air anymore, we're trying to liquefy a substance that nature keeps gaseous under all terrestrial conditions. The development project took 3 years and consumed more resources than any of our previous research efforts. Carl had to design entirely new refrigeration systems capable of reaching ultra-low temperatures reliably and efficiently. He had to develop materials that could withstand the extreme temperature variations without becoming brittle or losing their sealing properties. He had to create insulation systems that could prevent heat transfer at temperature differences greater than anything previously attempted. Most challenging of all, he had to solve the practical problems of handling a cryogenic liquid that would instantly flash back to gas if it came into contact with anything warmer than minus 160 degrees. The secret to successful innovation, Carl told a gathering of young engineers in 1905, is not genius or luck or inspiration, though those things can certainly help. The secret is persistence in the face of failure, curiosity about phenomena that others take for granted, and willingness to challenge assumptions that everyone else accepts without question. When I first started trying to make ice with ammonia, everyone knew it was impossible. The experts had very good reasons why it wouldn't work. But I didn't accept their reasons. I tested them. I experimented with different approaches. I learned from every failure and applied those lessons to the next attempt. Eventually, I succeeded not because I was smarter than the experts, but because I was more persistent. And once I succeeded, the impossible became not just possible, but routine. That's how all real progress happens. Someone refuses to accept that something can't be done and keeps working until they prove everyone else wrong. By 1910, Carl von Linde's technologies were so thoroughly integrated into modern life that most people took them for granted. Fresh food was available year-round in cities thousands of miles from where it was produced. Industrial processes that had once been impossible in warm climates were operating efficiently in tropical regions. Scientific research was being conducted at temperatures that had never existed naturally on Earth. The global economy was being powered in part by natural gas that had been liquefied for transportation using Carl's methods. Millions of people were employed in industries that existed only because reliable refrigeration made them possible. And yet, for all these achievements, Carl remained fundamentally the same person I had met in that chaotic Munich workshop 34 years earlier. Endlessly curious, deeply committed to solving problems through scientific understanding, and genuinely excited about the possibility of making life better for as many people as possible. "You know what I'm most proud of?" he said to me during one of our last conversations before his retirement in 1910. "It's not the patents or the profits or the awards or the recognition. It's the fact that somewhere right now, there's a child eating fresh fruit that was grown on the other side of the world and transported here without spoiling. There's a patient receiving medicine that remained effective because it was kept at the proper temperature. There's a family enjoying a cold drink on a hot summer day. Those people don't know my name, and they don't need to. But their lives are a little bit better because of work we did in this laboratory. That's what real success looks like, making the impossible become so routine that people forget it was ever impossible. Carl von Linde passed away in 1934 at the age of 92, having lived to see his inventions become essential infrastructure for modern civilization. But his legacy extended far beyond the specific technologies he had created. He had demonstrated that individual inventors could still make fundamental contributions to human welfare in the modern age. He had shown that scientific curiosity could be combined with practical application to create enormous value for society. He had proven that persistence and systematic investigation could overcome obstacles that initially seemed insurmountable. Most importantly, he had established principles for innovation that would be applied to countless other challenges throughout the 20th century and beyond. The methods he pioneered for refrigeration research would be used to develop electronics, aerospace technology, medical devices, telecommunications, and dozens of other fields that didn't even exist when he first started making ice with ammonia. Chapter 9: The Invisible Revolution. As I sit here today, more than a century after Carl von Linde first fired up his ammonia compressor in that cluttered Munich workshop, I'm amazed by how completely his invention has disappeared into the background of modern life. You see, that's the mark of a truly successful technology. It becomes so essential that people stop noticing it exists. Carl's refrigeration systems are running quietly in the background of virtually every aspect of modern civilization, but they're invisible to most people because they work so reliably. Think about it for a moment. When you open your refrigerator to get a cold drink, do you think about the ammonia compression cycle that makes the cold possible? When you buy fresh meat at the grocery store, do you consider the chain of refrigerated transportation and storage that kept it fresh from the slaughterhouse to your table? When you take a life-saving medication, do you realize that its effectiveness depends on temperature-controlled manufacturing and distribution? Of course not. These systems work so well that you don't have to think about them. That's exactly what Carl intended. But the invisibility of refrigeration technology also means that most people don't fully appreciate how revolutionary it was, or how dramatically it changed human civilization. So let me paint a picture for you of what the world looked like before Carl's invention became widespread. In 1870, the global population was approximately 1.3 billion people. The vast majority lived in rural areas and survived primarily on food they produced themselves or could obtain from nearby sources. Long-distance trade in perishable goods was limited to items that could survive extended transportation without spoilage: dried grains, salted meats, preserved fruits, aged cheeses. Cities were smaller and less densely populated than today, partly because it was difficult to supply urban populations with fresh food reliably. Industrial development was concentrated in regions with favorable climates because many manufacturing processes couldn't operate effectively in extreme heat or cold. Medical care was primitive by modern standards, not just because of limited scientific knowledge, but because many effective treatments couldn't be preserved or transported reliably. Vaccines, antibiotics, and other temperature-sensitive medicines were either unavailable or unreliable outside of major medical centers. Most importantly, people lived with constant awareness of seasonal limitations. Summer meant spoilage, waste, and foodborne illness. Winter meant scarcity and dependence on preserved foods. The rhythm of life was dictated by the rhythm of the seasons in ways that people today can barely imagine. By 1950, just 80 years after Carl began his refrigeration experiments, the world had been transformed almost beyond recognition. The global population had grown to 2.5 billion people, nearly doubling in 80 years. But more significantly, the distribution of that population had shifted dramatically. Cities had grown enormously, with many reaching sizes that would have been impossible to supply with food using pre-refrigeration technology. Global trade in fresh foods had exploded. Meat, dairy products, fruits, and vegetables were being shipped thousands of miles from producer to consumer as routine commercial operations. Seasonal limitations on food availability had largely disappeared in developed countries. Industrial development had spread to regions that had previously been unsuitable for manufacturing because of climate limitations. Medical care had advanced dramatically, partly because effective treatments could now be preserved, distributed, and administered reliably regardless of location or climate. Most remarkably, people had stopped thinking about temperature control as a luxury or convenience. It had become a basic expectation of modern life. But the transformation was far from complete. By 2000, another 50 years later, refrigeration technology had enabled changes that even Carl couldn't have imagined. The global population had reached 6 billion people, with the majority now living in cities that depended entirely on global food distribution networks for their survival. Fresh tropical fruits were available year-round in Arctic cities. Fresh seafood from every ocean was available in landlocked regions thousands of miles from the sea. Entire industries had emerged that existed only because of reliable temperature control. The frozen food industry was generating hundreds of billions of dollars annually. The pharmaceutical industry was producing temperature-sensitive treatments that were saving millions of lives globally. The electronics industry was using cryogenic processes to manufacture components that enabled modern computing and communications. Air conditioning, a direct descendant of Carl's refrigeration technology, had made it possible for major cities to develop in previously uninhabitable climates. Phoenix, Dubai, Singapore, and dozens of other major urban centers existed primarily because mechanical cooling made them livable. And still the revolution continued. Today, in the 21st century, refrigeration technology enables aspects of modern life that go far beyond Carl's original vision of preserving food and supporting industrial processes. Global supply chains for everything from pharmaceuticals to electronics depend on precise temperature control throughout manufacturing, shipping, and storage. Scientific research relies on cryogenic technology to create conditions that don't exist naturally anywhere in the universe. Space exploration uses liquefied gases, direct descendants of Carl's LNG technology, as rocket fuel. Medical treatments that seemed miraculous just decades ago, organ transplantation, gene therapy, cancer immunotherapy, all depend on refrigeration technology to preserve biological materials and maintain precise environmental conditions. Even our modern food system would be impossible without the infrastructure that Carl's inventions made possible. The average meal in a developed country contains ingredients from dozens of different locations around the world, all preserved and transported using refrigeration technologies that can trace their lineage directly back to that ammonia compressor in Munich. But perhaps the most remarkable aspect of this transformation is how it demonstrates the unpredictable nature of technological progress. When Carl first succeeded in making ice with ammonia, he was focused on solving immediate practical problems for local breweries. He had no idea that he was laying the foundation for global food distribution networks, cryogenic scientific research, liquefied natural gas markets, air conditioning systems, or any of the other industries that grew from his work. This is how real innovation works, not through grand master plans or visionary predictions, but through individuals solving specific problems and then discovering that their solutions have implications far beyond what they originally intended. Carl's story teaches us that the most important breakthroughs often come from combining curiosity about fundamental scientific principles with persistence in solving practical problems. He succeeded not because he had a grand vision of transforming modern civilization, but because he was genuinely curious about thermodynamics and stubbornly determined to make his ammonia compressor work reliably. The transformation of civilization followed naturally from those modest beginnings. Today, as we face new challenges, climate change, resource scarcity, global health threats, space exploration, we would do well to remember Carl's example. The solutions to these challenges will likely come not from grand theoretical breakthroughs, but from individuals and small teams who combine scientific curiosity with practical persistence to solve specific problems. And those solutions, like Carl's refrigeration technology, will probably have implications far beyond what their creators originally imagined. Chapter 10: The Man Behind the Revolution. As our story draws to a close, I want to share with you some thoughts about Carl von Linde, the man, not just Carl von Linde, the inventor. Because while his technical achievements were extraordinary, what made them possible was something more fundamental, a particular way of approaching problems and opportunities that anyone can learn from. I had the privilege of working closely with Carl for over 30 years, and I can tell you that he wasn't fundamentally different from other intelligent, dedicated people. He wasn't born with special insights into thermodynamics or mechanical engineering. He didn't have access to secret knowledge or hidden resources. What made Carl special was his attitude toward failure, his approach to learning, and his understanding of how progress really happens. Let me give you an example. Do you remember that first catastrophic demonstration for Baron von Hirsch, when the ammonia line failed at the worst possible moment? Most people in Carl's position would have been devastated. They would have seen it as proof that their idea was flawed, their approach was wrong, their efforts were wasted. Carl saw it differently. To him, the failure was information. It told him something specific about the weakness in his system. The ammonia line couldn't handle the stress of extended operation. It was a problem to be solved, not evidence that the entire project was hopeless. Every failure teaches you something you didn't know before, Carl used to say. The only real failure is giving up before you've learned what the failure has to teach you. This attitude toward failure was perhaps Carl's greatest strength as an inventor. He never took setbacks personally or saw them as evidence of his inadequacy. He saw them as natural and necessary parts of the learning process. I watched him approach every problem, technical, business, or personal, with this same mindset. When suppliers refused to sell him materials, he found new suppliers or developed alternative approaches. When competitors tried to undercut his prices, he improved his efficiency and reduced his costs. When new scientific discoveries challenged his understanding, he eagerly incorporated them into his work. Carl understood that innovation is fundamentally about learning how things work, learning why they don't work, learning how to make them work better. And he had an almost childlike enthusiasm for learning that never diminished, even as he became wealthy and famous. I remember visiting him in his laboratory when he was in his 70s, long after he could have retired to a comfortable life of leisure. He was working on some esoteric problem in cryogenic physics, surrounded by equipment that would have been incomprehensible to most people, as excited as a child with a new toy. "Why do you still do this?" I asked him. "You've already achieved everything you set out to accomplish, and more. You could spend your remaining years enjoying the fruits of your success." He looked up from his apparatus with genuine surprise. "Enjoy what?" "This is what I enjoy, understanding how things work, figuring out how to make them work better, discovering principles that no one has understood before. This is the most enjoyable thing I can imagine doing." That conversation helped me understand something fundamental about Carl's success. He wasn't driven primarily by money or fame or recognition, though he achieved all of those things. He was driven by curiosity, genuine, insatiable curiosity about how the world works and how it could be made to work better. This curiosity made him a natural teacher as well as a natural learner. Carl loved sharing knowledge almost as much as he loved acquiring it. Throughout his career, he mentored dozens of young engineers and scientists, many of whom went on to make important contributions of their own. "Knowledge grows when it's shared," he used to tell his students. "Every person who understands these principles becomes capable of discovering applications I never would have thought of." The more people who understand how refrigeration works, the more ways it will be used to benefit humanity. Carl also understood something that many inventors and entrepreneurs miss: the importance of building systems rather than just creating products. When he first succeeded in making ice with ammonia, he could have simply licensed the technology to existing manufacturers and collected royalties. Instead, he built a complete system: manufacturing facilities, distribution networks, training programs, service organizations that could reliably deliver refrigeration solutions to customers anywhere in the world. It's not enough to invent something, he explained to me during the early days of our company's expansion. You have to create the entire infrastructure needed to make that invention useful to ordinary people. The refrigeration machine itself is just one component of a much larger system that includes manufacturing, installation, operation, maintenance, and continuous improvement. This systems thinking was evident in every aspect of Carl's work. He didn't just design refrigeration machines, he designed complete solutions to temperature control problems. He didn't just discover scientific principles, he developed practical methods for applying those principles reliably. He didn't just start a business, he created an industry. But perhaps most importantly, Carl understood that true success comes from making a lasting contribution to human welfare, not from accumulating personal wealth or recognition. I was with him during his final years, as his health began to decline, and he started to reflect on what his life's work had accomplished. "You know," he said to me one afternoon as we sat in his garden, "I'm prouder of the farmers who can now ship fresh produce to distant markets than I am of the patents I hold. I'm prouder of the families who can now preserve food safely than I am of the awards I've received. I'm prouder of the industries that provide meaningful work for millions of people than I am of the profits those industries have generated. Those things will outlast me by centuries. The patents will expire, the awards will be forgotten, even the profits will be spent. But the knowledge we've created, the problems we've solved, the capabilities we've given to humanity, those are permanent contributions." Carl von Linde passed away quietly in 1934 at his home in Munich, surrounded by family and friends. The newspapers around the world reported his death as the loss of one of the great inventors of the industrial age, comparing him to Edison, Tesla, and other famous innovators of his era. But I think he would have been prouder of a different kind of obituary, one that focused not on his personal achievements, but on the millions of people whose lives were better because of the work he had done. Today, more than 90 years after his death, Carl's true monument is not any statue or memorial, but the invisible infrastructure of modern life that traces back to his curiosity about making ice with ammonia. Every time you open a refrigerator, every time you enjoy fresh food that was grown thousands of miles away, every time you benefit from a medical treatment that depends on temperature control, you are experiencing the legacy of a man who refused to accept that something couldn't be done. Carl von Linde proved that individual curiosity, persistence, and scientific rigor can change the world in ways that benefit everyone. His story reminds us that the greatest innovations often come not from trying to achieve greatness, but from trying to solve specific problems for real people. And perhaps most importantly, his example shows us that anyone, regardless of their background, resources, or circumstances, can make meaningful contributions to human progress by approaching problems with curiosity rather than cynicism, persistence rather than pessimism, and systems thinking rather than narrow focus. The world is full of problems waiting to be solved, opportunities waiting to be recognized, and innovations waiting to be discovered. Carl von Linde's greatest legacy may be the inspiration he provides to future generations of problem solvers who will carry forward his work of making the impossible become routine. So the next time you enjoy the convenience of refrigeration, whether it's a cold drink on a hot day, fresh food in the middle of winter, or any of the countless ways that temperature control improves your life, take a moment to remember the man who started it all. Remember Carl von Linde, who saw a problem, applied scientific principles to solve it, and in the process changed the world in ways he never could have imagined. And remember that you too have the potential to solve problems that seem impossible today, but that future generations will take for granted as natural parts of their daily lives. That, my friends, is how progress really happens. One curious person at a time, one persistent effort at a time, one seemingly impossible problem at a time. Thank you for joining me on this journey through the remarkable life and revolutionary achievements of Carl von Linde, the man who taught the world to steal winter and in doing so made modern civilization possible. Epilogue. the continuing revolution. As I finished telling you Carl's story, I realized that in many ways his revolution is still continuing today. The principles he established, curiosity-driven research, systematic problem-solving, persistence in the face of failure, are still driving innovations that would have amazed even his visionary mind. Scientists today are using descendants of his cryogenic technology to explore quantum physics at temperatures approaching absolute zero. Engineers are applying his thermodynamic insights to develop more efficient refrigeration systems that help combat climate change. Entrepreneurs are using his business model of creating complete systems rather than just individual products to build industries around entirely new technologies. The methods Carl pioneered in that Munich workshop are being used to solve problems he never could have imagined: preserving human organs for transplantation, creating superconducting materials for quantum computers, developing cryogenic fuel systems for space exploration. But perhaps the most important continuation of Carl's work is the inspiration his story provides to people who are facing their own impossible problems today. Somewhere right now, there's an engineer working on sustainable energy storage who faces obstacles that seem just as insurmountable as Carl's ammonia leaks seemed in 1876. Somewhere right now, there's a scientist investigating new medical treatments who is experiencing failures that feel just as discouraging as Carl's failed demonstration to Baron von Hirsch. Somewhere right now, there's an entrepreneur trying to build a company around breakthrough technology who is facing skepticism and resistance just as daunting as what Carl encountered from the established ice merchants. To all of these people, and to anyone else who is trying to make the impossible become possible, Carl von Linde's story offers both inspiration and practical guidance. It shows us that the greatest innovations often come from the most modest beginnings. Carl didn't set out to transform global civilization. He just wanted to help local breweries make better beer. It shows us that persistence in the face of failure is more valuable than initial genius. Carl succeeded not because he never failed, but because he learned from every failure and kept trying. It shows us that systematic application of scientific principles can overcome obstacles that seem impossible. Carl didn't succeed through luck or inspiration, but through careful observation, rigorous experimentation, and logical reasoning. Most importantly, it shows us that individual efforts can have consequences far beyond what their creators originally envisioned. Carl's curiosity about making ice led to discoveries and applications that are still unfolding today, more than a century later. So as you go forward from here, remember Carl von Linde's example. Remember that every great achievement started with someone who was curious about solving a specific problem. Remember that every revolutionary technology began with someone who refused to accept that something couldn't be done. And remember that you too have the potential to be part of this continuing story of human progress, not through grand gestures or historic proclamations, but through patient curiosity, persistent effort, and systematic application of knowledge to solve real problems for real people. The impossible problems of today will become the routine solutions of tomorrow, thanks to people like Carl von Linde, and perhaps thanks to people like you. That's how the world really changes, one curious mind at a time, one persistent effort at a time, one seemingly impossible problem at a time. Carl von Linde proved it was possible once. Now it's your turn to prove it's possible again. The end.